Hi, this is John Whitaker for the Probability 1 class, and this is our 23rd video lecture, and I want to pick up where we left off last time. And what we had done last time ended with was an example, and so let me read the examples here on the board. But we were supposing that the number of people who visit a yoga studio each day is a Poisson random variable with mean lambda. And we suppose further that each person who visits is independently female with probability p or male with probability 1 minus p. What we mean here by the independence is that once one person comes in, that doesn't affect the likelihood of the sex of the next person that follows. And what we're asked to do is find the joint probability that exactly N women and M men visit the academy on a specific day. And so we're looking for the probability of big N equal to little n and or big N sub 1, if you will, equal to little n, and big N sub 2 equal to little n. And I summarize here just in terms of the notation what the answer was. So we had done this. We let N sub 1 be the number of women that come on that day, N sub 2 be the number of men, and big N be the total number of people. And so here, the probability that N sub 1 is equal to N and N sub 2 is equal to M, which is what we're looking for the joint probability mass function, we condition on N. And essentially what we're doing here is we're using the total law of probability here. And why do we want to condition on N? The reason we want to condition on N is because we know something about N, that it's a Poisson random variable with mean lambda. And so we work with this, we've done that, and we get this as our answer. Okay? Well, I want to make some observations about our answer. Okay, so some observations. Okay. Note that P sub N sub 1 equal to N is equal to the sum, as M runs from 0 to infinity, of P sub N sub 1 equals to N, and N sub 2 is equal to M. Okay, so the probability that big N sub 1 is equal to N is the probability that big N sub 1 is equal to N, and N sub 2 could be anything. So we run through all the cases, mutually exclusive events that's happening, sum them up. Okay. And that's equal to the sum, as M runs from 0 to infinity, of 1 over N factorial lambda P to the N e to the minus lambda P 1 over M factorial times 1 minus P times lambda raised to the M times e to the minus quantity lambda times 1 minus p. That's what we have. And that's from our answer for the problem. That we're having the sum of this as n runs from 0 to infinity. And then here we can see that this is a constant with respect to m, so I can pull it out. So it's 1 over n factorial lambda p to the n e to the minus lambda p. This summation is m runs from 0 to infinity 1 over m factorial, 1 minus p to the lambda, to the m, e to the minus lambda times 1 minus p. Then what I want you to notice is that this quantity that we're summing up here, this is a PMF for a Poisson random variable, okay? And its parameters, if you will, are 1 minus p times lambda, parameter is. And so when you sum up from m running from 0 to infinity of the PMF, you just get 1. So this is equal to 1 over n factorial, lambda to the p, lambda times p to the n, e to the minus lambda p. Okay, and so when we look for this is the PMF for n sub 1, and when you look at this is the PMF of a Poisson random variable. So let me write that down. So, n sub 1 is a Poisson random variable with parameter lambda p. Okay. 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 Similarly, n sub 2 is a Poisson random variable to do the same type of work with parameter. It would be lambda times 1 minus p. Okay? And that told us that n sub 1 and n sub 2 in this case are independent. As f of n sub 1 of n times f of n sub 2 of m, that's equal to the joint evaluated at n m. Okay? So that's what we have. Well, we can extend this result, or not, extend this example to be a fact. In particular, here's what we have. So suppose each of a Poisson number of events is identically is independent classified as either type 1 or type 2, either being So I should say type 1 with probability P. Or type 2 with probability 1 minus P. Then the number of type 1 and type 2 events are independent Poisson random variables. Okay. With parameters it's lambda p and it's 1 minus p, or lambda times 1 minus p, respectively, for type 2, the number of type 1 there. And this fact, the proof of it is in the work that we did with the previous example. However, this fact can be extended, and I'd like to go through the extension in detail. So just as the comments will be very clear, the proof of this fact, the previous one I just looked at, okay, is in the work of our previous example. Here is the fact that I'd like to list next. That's the extension. What we just said. So let's suppose each of a Poisson distributed, I should say, number of events n with mean lambda is independently classified as being one of k types okay, with probability with the probability that it is type I being p sub I, and here I is 1, 2, all the way up to k. There's k types. Okay, and one thing to say about these p sub i's, if you sum them all up, you'll get 1. So if n sub I is the number that are classified as type I, then n sub 1 up to n sub k are independent Poisson random variables with parameters lambda sub pi. That's the statement of the fact, and we are going to prove this. Even though it's very similar to the work we did in the example, I just think it's worth going through again. Okay, so here's the proof. Note the probability that n sub 1 is equal to little n sub 1, n sub 2 is equal to little n sub 2, all the way up to n sub k is equal to little n sub k. That can be rewritten if we condition on big N, the total number, okay? That's equal to the sum as I runs from 0 to infinity of p n sub 1 equal to little n sub 1, n sub 2 equaling little n sub 2, and all the way up to big N sub k equaling little n sub k, given big N equals to I times the probability that big N equals to I. And that's what we have. Okay. Well, the thing to notice here is that for all the times that I doesn't equal to the sum of little n sub 1 plus with little n sub 2 all the way up to little n sub k, then this probability is going to be equal to 0. So we're only getting one non-zero term in this sum, and that's the probability that n sub 1 equals to little n sub 1, n sub 2 equals to little n sub 2, all the way up to n sub k equals to little n sub k, given n equals to n1 plus n2 all the way up to nk, and then the probability, here I'll write this down here, times the probability that n is equal to n sub 1 plus n sub 2 plus all the way up to n sub k. Okay, here that's the same thing as this first probability, conditional probability I'll leave alone. N sub 1 equals to little n sub 1, n sub 2 equals to little n sub 2, big N sub k equals to little n sub k, given n is equal to this sum, times, all that times, and here, remember n is Poisson distributed, and so this would be e with a parameter lambda. E to the minus lambda, lambda to the n sub 1 plus n sub 2 plus all the way up to n sub k, adding that, and then all that divided by n sub 1 plus n sub 2 plus n sub k factorial. That's a Poisson's PMF, and we're evaluating it at the sum of the little n sub 1's, n sub 2, all the way to n sub k's. Now, I've gone ahead and left it. Let me go back. I'm sorry. I'm going to go back for a second. Yes, sure do. Now look, this goes to, what I'm about to explain, to something that kind of generates the binomials PML. But here's what we're thinking here. Look, we know we've got this many objects, this many things happen, okay? And we're saying, how do we split them up? Let's probably, we've got n sub 1 of type 1, n sub 2 type 2, and all the way up to n sub k of type k of them, when we know the sum of them happen. You know? And so what we do is we say, well, how many ways could we get n sub 1 of type 1 or n sub 2 of type 2? And so what you do is you'd say, well, we have n sub 1 plus n sub 2 plus all the way up to n sub k number of events that happen. If we want the number of ways of them that were n sub 1, that would be the number of ways we could put those down. In those n sub 1 plus n sub 2 plus all the way up to n sub k spaces, if you will, for which n sub 1 could occur, or type 1 could have occurred. You choose out of the n sub 1 plus n sub 2 plus all the way up to n sub k, you choose n sub 1 of them to have type 1. And then you would multiply that by the probability that you got type 1. And then you would say, well, we'd like for the rest, or for out of the rest of them, we'd like n sub 2 of them to be, we'd like n sub 2 of them to be type 2. And so we would take, out of the rest of them that are left, the space that they're left, we choose n sub 2 of them, and then we multiply that by the chance that we got type 2, and so forth. So what that yields is the following. Remember in our work, in our example, we had binomial, because there were only two types there. Here, this is going to be equal to n sub 1 plus n sub 2 plus n sub k, choose n sub 1, p sub 1 to be n sub 1, and then it's going to be n sub 2 plus n sub 3 plus all the way up to plus n sub k, choose n sub 2, times the p sub 2 raised to the n sub 2, and then times, and we're going to keep going. The last one is going to be this multiplication. The last one is we're going to have n sub k, we choose n sub k, times p sub k raised to the n sub k. Okay. And then, don't forget, we still have that e to the minus lambda, and then it would be lambda, if you will, to the n sub 1, lambda to the n sub 2, times lambda to the n sub k, all over, this was n sub 1 plus n sub 2 plus n sub k factorial. Okay? Now look, when we start expanding these choosings, these combinations, the first one's n sub 1 plus all the way up to n sub k factorial over, here you'd have this quantity minus n sub 1, so that's n sub 2 plus all the way up to n sub k factorial, and then times n sub 1 factorial. And then it's p sub 1, n sub 1. And then this guy is going to be n sub 2 plus n sub k factorial all over, when I take this quantity and subtract n sub 2 from it, I'm going to have n sub 3 plus all the way up to n sub k factorial, times, it'll be n sub 2 times p sub 2 to the n sub 2, times, and we'll keep going. And the one right before this, let's see, that would be n sub k minus 1 plus n sub k factorial all over, it would be n sub k factorial, okay, that's what we have left, and then n sub k minus 1 factorial, and then this last term, where is it? Right here, and times, and here this is just 1, well this, sorry, I made a mistake here, it should have p sub k minus 1 raised to the n sub k minus 1. And then finally, times, this is 1, so it's just p sub n sub k, p sub n sub k, and then this is just k. And then here we have the same quantity, e to the minus lambda, lambda to the n sub 1 times lambda to the n sub 2 times lambda to the n sub k, all over this n sub 1 plus n sub 2 all the way up to n sub k factorial. What happens is that there's a lot of cancellations that occur between the factorials. This n sub 1 all the way up to n sub k being added factorial is appearing right here in the denominator. And then this n sub 2 plus n sub k factorial is appearing, it's in the denominator, but it's appearing here. Okay? And so what we're left with are these n sub 1s. Okay? All the way up to this last two. And so, the way that we can represent what we have in a nicer form is it's equal to, okay, so this is, if you will, 1 over n sub 1 factorial, n sub 2 factorial, all the way up to n sub k factorial. That's what's in the bottom. And then, what we have is we're going to have e to the minus lambda, and then we're going to have lambda sub p sub 1 raised to the n sub 1. Okay? And then lambda p sub 2 raised to n sub 2, all the way up to lambda times p sub k raised to the n sub k. That's the way that it can be rewritten. Okay? Now, the next thing I'm going to do is work on that e to the minus lambda part. And so, that's the same thing as 1 over n sub 1 factorial. This is the same, times n sub 2 factorial, all the way up to the multiplication of n sub k factorial. The e to the minus lambda is really e to the minus lambda, the lambda times 1, but minus lambda times 1. But that 1 is the same thing as the sum of the p sub i's. I running from 1 to k, because remember that was equal to 1. And then this lambda p sub 1 to the n sub 1, all the way up to lambda p sub k to the n sub k. And so here, this is 1 over n sub 1 factorial, 1 over n sub 2 factorial, times 1 over n sub k factorial. Here, this will be e to the minus lambda p sub 1 plus lambda times p sub 2. I should say minus lambda p sub 3. But when you have a sum in the exponent, you can rewrite this as minus lambda p sub 1 times e to the minus lambda p sub 2. That's right. And then all the way up to e to the minus lambda p sub k. And then times lambda times p sub 1 to the n sub 1. All the way up to lambda times p, that's a lambda, times p sub k to the nk. Okay? That's what we have. Okay? Okay. And this can be written with notation indicating product. This represents a product, like the sigma represents a sum. This represents a product. As I runs from 1 to k, this would be 1 over the n sub I, e to the minus lambda p sub I, lambda to the p sub I raised to the n sub I. That's one way of rewriting or expressing what we have above. Okay.
Okay, what we're going to look at next is the PMF for n sub 1. Well, the way we would express that, that's the sum as n sub 2 runs from 0 to infinity, sum n sub 3 runs from 0 to infinity, and so forth. Sum all the way from n sub k running from 0 to infinity. The 1 over the n sub 1 factorial all the way up to n sub k factorial. Again, we're going to have the lambda p sub 1 to the n sub 1. I've run out of room. Let me put it down here. Times, it's going to be lambda p sub 2 to the n sub 2. This should be n sub 1. All the way up to lambda p sub k to the n sub k. Here I wrote down p sub 1, but it should have been 2 here. 2. This should have been 3, 3, all the way up to n sub k. We don't have n sub 1 involved. And then e to the minus lambda p sub 1, e to the minus lambda p, all the way up to p sub k, and then that's it. Okay, that's what we have. Okay. All right, now the n sub 1 is not involved in this sum, so I can pull that out. 1 over n sub 1 factorial. The e to the minus lambda p sub 1 I'll pull out. And then I'll also pull out the lambda. I made a mistake. It should include lambda p sub 1, n sub 1. I made a mistake. Okay, it should be 2, n sub 2. Okay, we sum, that's silly of me. We sum, we have k minus 1 summations here. We sum the joint PMF with all of these sums. So the PMF includes the p sub 1. So I don't know why I didn't have them in there. I wasn't thinking. But I can pull them out. So lambda p sub 1, n sub 1, because I can pull them out because n sub 1 is constant with respect to each one of these sums. And then we have these sums here, n sub 2 to 0, infinity, all the way to the sum, n sub k equals 0 to infinity. It would be 1 over n sub 2 factorial, all the way up to n sub k factorial. And then I have this lambda p sub 2 to the n sub 2, all the way up to lambda p sub k to the n sub k. And then all that's times e to the minus lambda p sub 1, all the way up to e, no, not p sub 1, we're taking that out, p sub 2, e to the minus lambda p sub k. We had taken out the p sub 1. There it is. Okay. Now look, this sum can be broken up by pulling out constants with respect to each one of the summations here. And what you're going to get is a sum of Poisson, the PMFs for Poisson distributed random variables, and you're just going to end up getting 1 for all of this. Okay? So if you will, I'll write it down as 1 over n sub 1 factorial e to the minus lambda p sub 1, lambda p sub 1 to the n sub 1, and then you're going to get eventually the sum is n sub 2 goes from 0 to infinity of what? 1 over n sub 2 factorial, lambda sub p, lambda times p sub 2 raised to the n sub 2 times e to the minus lambda p sub 2, and then that guy times, and there's going to be a bunch of sums just like that, and the last one is n sub k, running from 0 to infinity, 1 over n sub k factorial, lambda p sub k raised to the n sub k, and then e to the minus lambda p sub k. And as I said, each one of these sums are the sums of the PMF of a Poisson distributed random variable. And so what we end up getting here is 1 for each one of those sums. So our answer is 1 over n factorial e to the minus lambda p sub 1, lambda p sub 1 to the n sub 1. And that's what we get for the PMF of, it should have said n sub 1. Gosh, what a mistake. Okay, that's what we get for the PMF of the random variable n sub 1. And this is Poisson, this PMF is, and with parameter lambda p sub 1. And similarly, for each one of the n sub i's, for each I, 1 to k, the probability that n is equal to n sub I is equal to 1 over n sub I, this should say n sub I here, factorial lambda p sub I to the n sub I times e to the minus lambda p sub I. Okay. So that gives that the n sub i's are independent because their multiplication of the PMS of each one of them equals to the joint PMS. So they're independent, Poisson distributed random variables. With parameters lambda p sub I, and that ends the proof. Okay, I now want to extend a way of computing conditional expectations, doing a conditioning on it. So we'll list a fact. So here, the conditional expectation of x given y to y, it can be rewritten in one of these two ways. It's the sum over little w of the expected value of x given big W is equal to little w, and y is equal to y times f sub w given y, little w given y, that sum, and that's if w is discrete. And it's equal to the interval from minus infinity to infinity of the expected value of x given w is equal to little w and y is equal to little y, okay, times the conditional probability density function of w given y, little w given y, dw. And it's that if w is continuous. Now, that's what we have. Let's do the proof of that. So, before I do the proof, let me say, although this fact is true in all cases, for the types of random variables that are involved. What we'll say is that we will only prove the fact in 2 cases. I'll say out of the 6 cases. Hold just a second. Yeah, so it's 8 cases. Yeah, 8 cases. And so the cases have to do with whether x, with the discrete or continuous nature of x, y, and w. And so here, let's talk about for case 1. So the statement's true no matter what, but we'll only look at 2 cases. That's when they're all continuous or all discrete. So case 1 is x, y, and w are all discrete. Now, what we're going to do is look at the right-hand side of this equation. So w is discrete in particular. So when we look at, so we note this sum over w of the conditional expected value of x given w equals to, this is a little w here, w equals to little w and y equals to little y times f sub y, I'm sorry, w given y of, here I'll say, I normally write down y w. No, it's w given y. There we go. So when we look at this, what will we get? Okay, that's equal to a double sum. So it's over w over the x values of x m sub x given y and w, x given y and w, and then times, so the conditional probability density function of w given y, that can be thought of in terms of symbols, f of yw over f y. Okay, this is equal to a sum over w, sum over x, and here this is x. Let's replace this by what it's equal to, which would be f evaluated x, y, and w, the joint PDF of all 3. And here this will be f, the joint between y and w, times f yw over f sub y of y. That's what we get. This is equal to, well, there's cancellations that will occur, so let's do that. X, here I have f of x, comma y, comma w, over f sub y, y. And now, let us reorder the summations. Here, let's put x, then w, x, f of x, y, w, over the PMF of y. So that's going to be equal to, well, I can take out the x that's in front because it's constant with respect to w, and then sum over w of f of x, y, w over f sub y of y, and that's going to equal to the sum over all x's of x. And when we sum over w, the y here is constant, so we just sum this part. That would be f of x, y over f sub y of y. That's what we get. And then that is nothing more than the conditional expectation of x given y. And that was the left-hand side of what we wanted to show. So the statement is true when we're having three discrete random variables. Well, the same thing happens with continuous, but let's look at it this time. So case 2, x, y, and w, as random variables, are all continuous random variables. So we look at the right-hand side of the statement we're trying to prove. So note, the integral from minus infinity to infinity of the conditional expected value of x given, w equals to little w, and y equals to little y, times f of w given y, okay, dw. That's what we're looking at. Look at that. What's it equal to? Well, that's going to be equal to an integral from minus infinity to infinity, and then another integral for this expected value. And it's going to be x from minus infinity to infinity. Here, this will be f sub x given w and y. Here it's x given point, I'll say yw. And then times f sub y given, w given y, w given y, dw. All right, we'll finish this off just here in a minute or two. And that's equal to, we're very close to here, this is the double integral from minus infinity to infinity. I made a mistake. Let me go back. It's a small mistake. Okay, the small mistake is we've got this second integral, and so what I need here is this needs a dx with it. Okay, so we think of this as kind of an inner integral. Okay, so let's make that change. I'm sorry. Now, this is equal to an integral, then an inner integral from minus infinity to infinity, x, and then here, if you want, you can have f of x, w given y, w and y, x given y, w. Okay, then this f of w given y, I can put it inside that integral and rewrite it as f of y, w over f sub y of y, just like what we had before. And then I need dx and then dw. Okay? So here we'll rewrite this one, minus infinity to infinity. Inner integral from minus infinity to infinity, x, this is f of x, y, w, over f of y, w. This is f yw of yw over f sub y, y, dx, dw. And then there's cancellations that occur. So integral from minus infinity to infinity, integral from minus infinity to infinity of x. These two guys cancel. I'm left with f of x, y, w over f sub y of y. And then here's dw, dx dw. And then we're going to switch the order of integration. So I'm going to rewrite this as integral from minus infinity to infinity, minus infinity to infinity. I'm going to rewrite them for the order, so I can pull out the x, because x is going to be last. And here it's f of x comma y comma w over f, so y, y. And then this is dw dx. And this inner integral, this is a constant, the bottom is a constant. And when you integrate with respect to w of this, what you're going to get, because we're going to get an outer integral, minus infinity to infinity. We're doing the inner integral, or the integral of the joint with respect to one of the variables gives you the joint with the other two. So I have x, f of x comma y, f sub y of y, dx, and that's nothing more than the expected value of x given y. And that's what we're trying to prove. And so here we'll say that gives the conclusion of what we were trying to prove, the two cases. Ladies and gentlemen, that's enough for this video lecture. I want to thank you very much for your time and patience.